Welcome to Module 4, Lesson 7, Linear and Exponential Growth. So, linear growth versus exponential growth. We've learned about both linear and exponential functions, and now we're going to compare and differentiate between the two of them. So, linear growth increases by the same amount per step, right? You guys know that as the slope. It's the average rate of change, a constant rate of change. The formula is y equals mx plus b. An example of this would be saving $10 per week. Exponential growth increases by a constant percentage or factor per step. The formula would be y equals a times b to the power of x. And an example of this would be doubling bacteria population every hour. Here are some key differences between linear and exponential growth. So the rate of change. With linear growth, it's constant. So you're using adding or subtracting. Anytime the rate of change involves addition or subtraction of the same number, that's linear. And for exponential, it's increasing. So it's multiplying. The shape of the graph, for linear growth, it's a line. And for exponential growth, it's a curve. An example of each would be for linear growth, adding $10 to your savings each day, and for exponential growth, doubling your savings each day. Right? So anytime you see the words doubling, tripling, or halving, you should think exponential. Please pause this video and work on the Lesson 7, Level 1 problems in the workbook. In Level 2, we're going to look at some situations and determine whether they're linear or exponential. So which situation can be modeled by a linear function? Let's go through all of the choices and see what we think. So choice A says the population of bacteria triples every day. Well, I see the word triples, so I know that that's exponential. In B, it says the value of a cell phone depreciates at a rate of 3.5% each year. So it's going down, decreasing by a percentage, right? We know when the rate of change is a percentage, that's exponential. C says an amusement park allows 50 people to enter every 30 minutes. Well, that one seems linear. That one seems like a constant rate of change. Every 30 minutes, we're adding 50 people, right? It's the same amount every 30 minutes. So it looks like it's C, but let's just make sure that it's not D. D says a baseball tournament eliminates half of the teams after each round. So I see the word half, and I know halving is dividing, which means that it must be exponential. So the answer is C. Which scenario represents exponential growth? Again, let's go through each option and see what we think. A says a water tank is filled at a rate of 2 gallons per minute. So 2 gallons per minute is a constant rate of change, so that would be linear. B says a vine grows 6 inches every week. So 6 inches every week, the vine is growing by the same amount of inches. That would be linear. C says a car increases its distance from a garage as it travels at a constant speed of 25 miles per hour. Well, the word constant in the answer already gave it away, that it's a constant rate of change, which means that would have to be linear. And choice D says a species of fly doubles its population every month during the summer. So doubles, I'm seeing the word doubling, so I know doubling means exponential. So it has to be choice D. Please pause this video and work on the Lesson 7, Level 2 problems in the workbook. So let's look at a Level 3 expert problem. I give you this table here, and it shows the value of a particular car over time. Determine whether a linear or exponential function is more appropriate for modeling this data. Write an equation that models the scenario. Round your values to the nearest hundredth. So there are two parts to this question. First, we need to determine whether it's exponential or linear, and then we have to write the equation. So if you look at the values, right, the value in dollars, the Y column, the values are decreasing. And if you notice, right, every 5 years, the value of the car is going down by almost half, right? So that would be exponential, right? The values are decreasing by almost half every 5 years. So that wouldn't be a constant rate of change. It has to be exponential. Now we have to write the equation. So what do we know about the equation of an exponential function, right? The formula is y equals a times b to the power of x. So just like we did in the lesson about the center and the spread, we can use the graphing calculator to get our values of a and b to write our equation. So get your graphing calculators handy. If you need a moment, just pause this video and get your graphing calculator ready. So we're going to go to Stat, Edit. This time, since we had an X and a Y column, we're going to use L1 for our X values and L2 for our Y values. So L1 and L1, we're going to put 0, 5, 10, 15, and 20. Then we're going to move over to L2, and we'll put our Y values, which was 20,000, 10,550, 5,570, 2,940, and 1,550. Okay. So now we'll go to Stat, Calc. You're going to scroll all the way down until you see choice 0. It says right, exponential, right? Enter, 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 enter. And here you go, right? So they give you the form of the equation, y equals a times b to the power of x. Here's your value of a, right? We know that a is the initial value, the y-intercept, so we know that's 20,000. The table gives us that. And b is the value that we're looking for here, so we're just going to round that to the nearest hundredth and substitute it into the equation. So substituting our values into the equation, we get y equals 20,000 times 0.88 to the power of x. Please pause this video and work on the Lesson 7, Level 3 problems in the workbook. Once you're finished with the problems in the workbook, please move on to the next video for Lesson 8.